The modern passenger jet. It flies at over 600 miles an hour, high above the weather. It can cross the Atlantic in 6 hours, and it's the safest form of transport by far. It's 50 years since the passenger jet first transformed our world.
It was really breaking new ground. Nobody had ever built anything like this before. What it meant for the guy in the street was that he could fly almost as fast as a jet fighter at the time.
Today, the battle continues to design planes that are ever faster and more efficient. Designers are constantly testing new materials and pushing at the boundaries of aeronautical understanding.
When they see the swept blade, they'll go, gosh, that's different, because it will be so different to what they've actually seen before.
Is it as perfect as it can be? How close are we to building the ultimate passenger jet? This is the Airbus A330, one of the most advanced passenger jets in service. It carries 360 passengers, over 300 more than the first jet airliner. And a single Airbus engine produces enough energy to supply a small town. The modern passenger jet is a miracle of engineering. But the design journey to get here has been an extraordinary story of inventiveness and disaster. From the beginning, the dream of aircraft designers was to build a passenger plane that combined the comfort and style of old-world travel with high-tech, high speed. In the 1940s came an invention that would revolutionize air travel: the jet engine.
This was an exciting time. Jet engines really were the news. They were being featured all the time, jet aeroplanes being featured in the newspapers and in the news. They were breaking new records. This was a revolutionary mode of transport.
And the first passenger aircraft to use jet engines was the Comet.
It was the Comet which attracted most attention as it took off.
The Comet in one stroke, almost half the time that you could actually get to somewhere. For example, the first flight, the world's first ever jet passenger service from London Heathrow to Johannesburg in South Africa on May the 2nd, 1952, took 18 hours compared to 32 hours previously. So it really was a major step forward.
From the invention of the jet engine, designers have had one aim: to make it both powerful and fuel efficient. A state-of-the-art jet engine takes 15 days to build and costs around $10 million. It has two essential parts: the motor and the fan.
For any aircraft to fly through the air, it needs some form of propulsion, and the simplest form is a child's balloon. You fill the balloon with air, then when you release it at the nozzle, the air escapes, pushing the balloon along.
With a jet engine, the air is collected by a fan that's driven by the motor.
This fan collects about a ton of air a second, propels it rearward, and pushes the aircraft along through the air. The ton of air is collected every second, and that's enough air to empty probably 2 squash courts in a second.
To travel faster, designers knew they needed to get more air through the engine. This quickly became their holy grail. In 1950, a jet engine fan blade was about 12 inches long. Designers knew the simplest way to move more air through the engine was to increase the size of the fan blades. But as they increased the size of the blades, they were simply creating another problem for themselves. Bigger blades were heavier. So in the 1970s, the race was on to find a way of making these bigger blades lighter. The answer? Make them hollow. These hollow blades were fitted in 1984 on Boeing 757s and later the 747s and Airbus A320s. But making a hollow blade isn't easy. Designers at Rolls-Royce found that the two panels would flex and vibrate. To stop this happening, they came up with an ingenious solution.
The need was to have a blade made up of 2 titanium panels with a honeycomb core inside to stop the panels from vibrating together, so what I would call panting, so they're moving together relative to each other.
But hollow blades weren't the end of the story. In the 1990s, in search of the ultimate engine, Hilary Barton and her team looked to computer-aided design to improve the shape of the blade itself. They came up with a radical new design, a swept blade. And they managed to make blades lighter still by changing the way they are built.
The latest blade is manufactured from basically 2 sheets of titanium panel with a third one in the middle, so they come together, and that basically forms a sandwich with a filling in the middle.
Then a second manufacturing process works its magic.
Extreme heat is applied to the sandwich and an inert gas is pushed into the sandwich, and it causes the external panels to form, to blow out, to inflate.
And that makes the titanium core stretch between the 2 panels into a unique structure.
And in stretching, it forms a corrugated internal core which has like a zigzag form.
A form that makes this state-of-the-art jet engine both light and very strong. But it's the groundbreaking blade shape that Hilary Barton thinks catches passengers' attention.
I think to people that go and actually look at the front of an engine, when they see the swept blade, they'll go, gosh, that's different, because it will be so different to what they've actually seen before.
After 50 years of design improvements, the jet engine is more powerful than ever. But it also needs to be proof against a surprising hazard: birds. Since the earliest days of flight, birds have been a danger.
The very first bird strike actually happened to the Wright brothers back in 1908, where I believe it was Orville Wright's Wright Flyer hit a gull. The first fatality was in 1912 when Cal Rogers, who was also flying a Wright Flyer, had a gull entangled in his aircraft controls, and he unfortunately died as a result. And bird strikes have been occurring ever since.
With the advent of jet travel, things changed. Sometimes bird strike would bring the plane down, sometimes it wouldn't. Then, a plane crashed on takeoff at Boston Airport and 62 people died. When bird strike was suspected, ornithologist Roxy Laybourne determined to solve the mystery. She began to examine the remains of birds that had struck planes, trying to establish if there was a pattern to which birds were the most dangerous. But immediately, she hit a snag.
Frequently these remains are completely shredded. They've often been cooked due to the high temperatures involved. They're almost like shredded pipe tobacco in texture.
The usual bird identification techniques are useless with such mangled specimens, but the ornithologists were able to turn to the latest stereo microscopes to gather clues.
This can be done with even the most tiny fragments of downy feather from a bird. Then we can look at the microscopic structure of the bird's feathers, and we can compare this to reference material that we have here at the laboratory to match groups of birds with the unknown bird.
As more and more samples arrived in the lab, Roxy Laybourne began to identify a pattern. The crucial factor was not the size of the bird, but whether it was a bird that flocked, like gulls or geese.
Solitary species, birds such as kestrels, for example, that might hover over airfields, are far less hazardous to aircraft because they occur on their own. They can only ever hit one engine.
It was the multiple strike, more than one bird being sucked into an engine at once, that would bring a plane down. Armed with this new information, blade designers began to engineer their blades to counter the real threat birds posed. Every new blade is tested to withstand impact from a 4-pound flying goose. This Rolls-Royce blade is designed to dissipate the energy of impact. It flexes and only takes 2 rotations to return to normal.
Once it's rotated once or twice, the blade is returned to its start shape and is really hardly affected by the impact at all.
But this test only represents a single bird and a single blade. Can a complete working engine $10 million worth of cutting-edge technology survived the ultimate test, the worst-case scenario, a multiple bird strike. Before it can fly, every new jet engine must survive the ultimate test, a multiple bird strike. A fully working engine with a value of around $10 million is mounted in a test rig, and 6 chicken carcasses are fired at it.
Clearly, we can't move the engine forward at the takeoff speed of an aeroplane, so we have to fire the birds into the engine at that speed.
6 barrels use compressed air to fire the birds into the engine.
Now, the objective here is that the engine continues to operate and it mustn't lose more than 25% of power.
6 birds are fired. There's a slight note change as the blades flex, but the engine only loses 3% of its power, so this takeoff would have proceeded smoothly with no risk to the passengers on board. Thanks to the forensic detective work of ornithologist Roxy Laybourne in the 1960s, all jet engines are now engineered to withstand multiple bird strike. 50 years ago, the jet engine transformed air travel. Today, it's astonishingly powerful and super light. It's the beating heart of the passenger jet. Since the first flights in 1903, engineers had used paper, cloth, wood, and eventually aluminium to make aircraft. But to get the best out of a jet plane, it should fly at 35,000 feet, where temperatures are minus 40 degrees. This would test aluminium to the limit. (1952). The first commercial flight of the world's first passenger jet takes off.
Designed to fly at a speed approaching 500 miles an hour, it represents the first of a new generation of jet airliners.
To make passengers comfortable at 35,000 feet, the Comet had to be pressurized and light enough for the first generation jet engine.
Jet engines, the initial jet engines, were not as powerful as ones that came on later on, so they had to make the construction as light as possible.
To achieve this, Comet's designers made the aluminium exceptionally strong. They did extensive tests to confirm it could stand the stresses of pressurization. There was no hint of trouble. For a year, the Comet flew safely. Then in 1953, disaster struck.
During 1953 and 1954, the Comet unfortunately suffered a series of disastrous accidents.
The whole fleet was grounded, and accident investigators began to search for clues to what had gone wrong.
As parts of the Elba comet were recovered, they were immediately flown back to Farnborough, where the intricate job of identification and assembly began.
For months, they examined the wreckage from the Comet accidents and submitted a working plane to extensive testing. The fault they discovered has since become famous: metal fatigue. The Comet designers had chosen aluminium alloys that were very strong, but it turns out that this was precisely the problem.
Because the fatigue problem was not fully understood at that time, they would not have had the full knowledge that we have today about the fact that when you design alloys for very high strength, it could make them more prone to this fatigue cracking problem.
Intensive research into metals and how they behave in flight followed the Comet tragedy. It caused a step change in plane construction.
The lessons learned from the experiments and the investigation was that the metal needed to be thickened, and also some of the aluminium actually used need to be changed, and the lessons learned from that were put into the development of the Comet 4.
The alloys used in Comet 4 were the product of this intense research. Martin Painter is a true enthusiast. He's not only knowledgeable about the Comet, he's also got a bit of it in his garage.
Well, what we have here is 2 sections of a former BOAC Comet 4. The aircraft was part of the fleet that started the very first transatlantic jet services back in 1958, and I managed to pick up a couple of mementos.
A sample of Martin's memento was taken to be scrutinised by an expert. It was to prove impressive.
When we tested the Comet material, we're surprised at the high level of strength that we achieved on the tensile specimen. The Comet material is in fact comfortably within the current requirements for that type of alloy.
The strength-to-weight ratio of the aluminium alloy used to make Comet 4 is still the best it gets.
It's not surprising that this material is still used for the manufacture of aircraft today.
What the Comet disaster taught aircraft designers was not just the danger of metal fatigue. They also learnt to tailor their use of metal alloys precisely to the different parts of the aircraft.
So you would use alloys which are tailored for high strength in the top surface of the wing, and you would use alloys which have good fatigue properties in the bottom surface of the wing.
The Comet 1 tragedy shook aircraft designers to the core. It revolutionised their understanding of how a plane can be made lightweight, but also safe. A passenger jet can't be made entirely of metal. The pilot needs to see where he's going, and it's nice for the passengers to see out too. On the ultimate passenger jet, windows would be tough as steel and light as a feather. They haven't achieved it yet, but it's this goal that for half a century has driven glass manufacturers.
Back in the 50s, the technology was the limiting factor in reducing the weight. So they used the best available technology at that time, which was conventional air toughening.
Glass made this way had been used on propeller planes, but now everything had changed. Jet flight demanded glass that was lighter and stronger than this air-toughened glass. So the race was on for new ways to make glass stronger. The way to toughen glass is to get the heat out of it quickly. In the 1970s, 20 years of experimentation by Pilkingtons in Birmingham paid off. They came up with a radical new way of doing this. To this day, the key to how it works is a closely guarded secret.
The glass comes through on the tongue bar system. The furnace door then opens. The glass goes up into the furnace. It's up there for probably 2 to 3 minutes at around 600 degrees C. It then comes down out of the furnace, and then it goes down into the powder. It looks like a liquid, but it's actually a powder which is fluidized by air bubbling through it, which allows the glass to slide into it when it comes out of the furnace.
This remarkable powder is very effective at removing the heat and so toughening the glass. So what's it made of?
Unfortunately, I'm not able to tell you the formulation, the chemical formulation, because it's company confidential. So.
The latest technology can produce glass that is half the thickness of 1950s jet plane glass. And just how strong it is astonishing. In this one-off experiment, a vehicle weighing nearly 1,000 kilograms will be lifted off the ground. The whole weight will be supported on a single piece of glass.
This is a chemically toughened piece of glass. It's been toughened by immersing it in hot molten salts, and it's 8 millimeters thick.
The glass bar is placed into the lifting rig. The crane lifts the rig until all the slack has been taken out of the chains and supports. The next stage is for the 8mm glass bar to take the full weight of the car as it's lifted from the ground. The most modern technology, the most demanding conditions, a dead weight of around 1,000 kilograms on a single piece of glass. The ultimate jet needs materials that are light, strong, and tested to destruction. But what about the shape of the passenger jet? The body of the jet has hardly altered in 50 years, but the wings have been transformed dramatically. Changing the wing shape is a tool that designers can use in their ongoing battle to make jets ever faster and more fuel efficient. Where the Comet had wings that were at right angles to the fuselage, by 1960, jet wings were at quite a different angle.
The first generation jet airliner wings were basically similar to the ones that were used on the propeller aircraft. What was needed was a wing that would limit the increase in resistance as the aircraft flew faster and faster with jet engines.
These thinner and more swept back wings enabled jets to fly faster. But as the planes flew ever faster, designers discovered they had created a new problem to grapple with. When any aircraft is flying, the air moving over the top of the wing travels faster than the air going underneath. As jets approached the speed of sound, something started happening on the tops of the wings that was very worrying.
The airflow over the top of the wing would actually go faster than the speed of sound, and would, somewhere on the top of the wing, you would get a strong shock wave, which give a lot of drag and is unacceptable. You must fly with very little shock drag on the wing.
To eliminate drag, Jeff Jupp and his colleagues experimented in the wind tunnel. First, they increased the sweep of the wing still further.
It was realised that by sweeping the wing backwards, rather like on this more modern aircraft, the A330, see the wing is not perpendicular to the fuselage but is now swept back. That also helped to reduce this problem of the shock waves formation as you fly faster.
Over more than a decade, they continuously modified the shape of the wings until at last they cracked the puzzle.
We were able to use the new computer programs to design the airfoil theoretically and then check it out in the wind tunnel to just check that we got what we were designing. And indeed, the results were very good.
They had designed the supercritical wing.
It takes a little bit of thinking about that the flow is actually supersonic over much of the wing, even though the aircraft is still flying below the speed of sound. And this is done still without getting these severe shock waves, which would give uneconomic flight.
And this ingenious technological marvel is now the design choice of aircraft manufacturers everywhere. Modern wings have achieved the ultimate combination: higher speed for less fuel.
The Comet really did usher in a totally new form of transport.
And ever since, aircraft designers have been refining that basic concept. This may be the final variation on the theme: the 800-seat double-decker Airbus A380.
This is a very large aircraft. It is probably getting pretty close to the maximum size of aircraft that we would envisage with today's materials and techniques.
Radical alternatives are being explored, but for now, this is probably as close as it gets to the ultimate passenger jet.